So this will be a brief description of manometers, which are really important in hydraulic engineering. And just to review the concept of force, um, how it's related to pressure. In this case, this is the shear stress, which is a sort of same units as pressure, but it's shear times the area. So force divided time area. And then whenever we have normal stress, which is pressure as well, then the notation that you're used to, it would be sigma, force over area. Of course, we measure pressure, and it's a normal force exerted by a fluid per unit area, and you can have several units, and we will see in the lab some pressure gauges. Now, there's two things that are really important, and it's to understand the definition between absolute pressure and gauge pressure. And of course, the gauge pressure could also be a vacuum pressure. So the actual absolute pressure is the actual pressure at a given position, whereas the gauge pressure is the difference between the absolute and the local atmospheric pressure. Most pressure measuring devices are calibrated to read zero. So what happens is that for atmospheric pressure, if you have a gauge meter, it will not read the atmospheric pressure, but the actual pressure inside that container, excluding the atmospheric pressure. A vacuum pressure would be, of course, below the atmospheric pressure. So 1 atmospheric pressure, 1 atmosphere, that's how we call it. So let's see the easiest case, which would be this. Here you have your atmospheric pressure and then a gauge pressure. So if you add them, you have the absolute pressure. So in that case, whenever you have a P absolute, of course, you'll have absolute pressure that it's equal to gauge plus atmospheric, and you have your P abs larger than your atmospheric pressure. Now, in the case of a vacuum pressure, what happens is that it's less than atmospheric pressure. So here is your atmospheric pressure, and now the vacuum pressure is going to be less. It's like a vacuum cleaner. We talked about that. Now, in our definition that I wrote here, what happens is that if the gauge pressure is negative, then your absolute pressure is going to be a negative value plus the atmospheric pressure. And so now it's this equation here. So all you have to remember is that vacuum pressure is a negative pressure, because it'll be less than atmospheric. I hope that quick description helps. So we know already the pressure of water with depth is rho GH, and this seems kind of redundant at this point, but you'll see how whenever we deal with manometers, these can get confusing. So here is our pressure, and as we go down below the surface, the pressure increases as the depth increases in this case. Okay, so but you go down and pressure increases. Okay? Whenever we look at pressure and how it changes with depth, then we know that at a given depth the pressure will be constant. So it doesn't matter the shape or form of the container, as long as you have the same fluid, the pressure will be constant at a constant depth. So you have here at the surface atmospheric pressure, and then this would be your absolute pressure. It would be the atmospheric plus the gauge. So this here really is the gauge pressure. Or one thing is, let me erase this. Whenever we have different shaped containers, sometimes we think that the pressure will change, but that's not the case. Okay, so whenever we look at this situation, here you have PA, and it's at the same level, but you have the same fluid on top, so the pressure is the same. Here you have the same pressure, here you have the same pressure, same pressure, same pressure. If we have a different fluid, it's not the same. So like here, H and I are at the same level. Here I have mercury, and here I have water. So the pressures in H and I are not going to be the same. Okay? So if you have a manometer, a simple manometer used to measure average temperatures, so we have here your P atmospheric, and then here you have your H, so you're going down in depth, so it's P atmospheric plus raw GH. And then whenever you come here, on this side is the same pressure, right? And then here you have the P gas, and it's a gas, so the pressure is all the same. So this would be the pressure that the gas exerts. Now, reviewing the same concept, what I'm going to do is, let's go from point 1 to point 2 to calculate either P1 or P2. So I have P1, and now I'm going down here. So I say, okay, times the specific weight of the water times H1. And remember, so here is water. I have the same pressure as here. Now, if I have the oil now, which is here, is going to be the same pressure as here. So this here in the interface is almost the same pressure. I'm going to assume it's exactly the same. So now I'm going down. So now, of course, I add pressure, and in this case, I have oil times H2. And then now I'm here in the interface, and I'm going up. So, and this is mercury. So it's the density, a specific weight of mercury times A3, and this is going to be equal to P2. It doesn't matter if you go from left to right or from right to left. You erase and go from the other position. So now I say, okay, P2, and I'm going down plus, and it's mercury, so mercury times H3. So now here the pressure is the same, but I'm going to go up, and this is H2, but it's this oil, so I'm decreasing in depth, so it would be minus E oil times H2. So now I move here. I already used H2, the depth I only use once. Now I'm going to go up in the water plus gamma water H1, and that's going to be equal to P1. So I can calculate P1 or P2, and then the other thing is that if they ask for P1 minus P2, then of course use either one of those definitions. For example, I say P1 minus P2 equals gamma mercury H3 minus gamma oil H2 plus gamma water H1. So sometimes you don't have to know specifically what's P1 and P2, but you know the difference. Now here I have P1 minus P2, so if I get this value here and I get a positive value, then P1 is larger than P2. But if I get a negative value, then I know that P2 is larger than P1 if I have negative. Okay? The manometer is also used to measure pressures across a flow section, and that comes from the manometer. So in this case, from point 1 to point 2, what you have is differences in elevation. You have A and H. You look for those differences, and then you have, in this case, liquid 1 and liquid 2, which we usually use mercury. So the expression then it's P1 plus the density 1 P8 plus H. In this case, we went from P1 and went all the way here, and then you go up, and it's this expression minus, and then you go up again, and this is the minus. And then whenever this expression is simplified, the difference in pressure is going to be rho 1 minus rho 2, or rho 2 minus rho 1 times the 8. But it's the same principle.